So there's a homework assignment due on Friday, right? So it's all about stick diagrams, a lot of practice. Oh wait, it's Friday midterm exam. It'll be a 1 hour exam, or 55 minutes actually in the class. Let's take a look. Yes, scheduled there on Friday because the midterm is due next Monday. I don't have to use a midterm exam for the grade, right? But it's just better, more comprehensive data that can be reflected by the midterm grade. So nothing is going to be on the notes and homework assignments and lectures. Okay, everything will be exactly what I covered here. We'll just change the numbers, change the logic expressions. I won't just go back to textbook and find out some of the end of the chapter problems for guys that never covered in the class. I won't do that. I was a victim of that kind of professors in college, so I know how that feels.
I can do all the problems in class and you look at the homework and it's like, what in the world?
Yeah. Oh, that one works. Great. Yeah. I believe some of the courses say the students just to keep hitting the buttons at the bottom for some reason. Would you be comfortable taking it on Friday? Any concerns or problems? I haven't made it yet, but you can imagine there will be. Since we have so many quizzes, if you put the problems and the quizzes together, it's probably a 55 minutes exam. It'll be very similar. So this semester is slightly different from the last year. I gave you guys more quizzes instead of homework assignments. No differences actually. It's just the same set of problems. So I think you guys just need to review the quizzes and homework assignments up to stick diagrams, I think. So including this one, because you will finish it before the midterm exam on Friday, right? So which means you should be able to ready to do stick diagrams in the midterm exam. So the only thing is I haven't graded yet, so I didn't give you the feedback on it. But if you have any questions you are unsure about for the in the homework 4, you can ask me during the office hours or anytime if I'm in the office. Okay. Make sure everything on this one is clear. Just make sure you can do it, something similar to this, right? If you have something, if you have ungate, doesn't have a bar on top, what should you do? Put a bar on top. But it won't be a one-liner, right? Can I make a one-liner for ungate? 2 bars. How do you make a one-liner for the ungate? Yeah, so just like what we did in the past week, right? For just a simple ungate, how can I make a one-liner? This seems to be super simple, right? Yeah. Then what? Yeah, that's right. So it becomes. The signals you have, yeah. Okay, now let's take a look at the quiz from Friday. I'll change the logic expressions for you guys so you can retake it. Okay, for the ones who didn't take it on Friday. I'll make it harder. Assume you watched the video, hopefully. Okay. I didn't see many issues in the quiz actually from the 3 of you guys. So for the 3 input, you can just directly start from this, or you can combine them or factor out A. But let's do just directly start from this equation or a logic function. ABC, AD, so ABC are in parallel PMOSes on the top. Um, and ABC in series for the NMOS. AD. So everyone made it right until, up to this step. But for the layout, there was a little tiny issue, but not really major. Definitely, if you only have two stages, we know it's going to be doable for one liner. So I'll just directly draw it. 5 transistors, I need 6 nodes. Three on the top in parallel. Remember the pattern for 3 parallel transistors, right? Okay. And then 2 in parallel. You have to start from this one because in the one liner it already made the connection. Okay, you have to start from here. For NMOS, so let's figure out which is A, which is B, C, D first before we draw this output. So you don't really have choices, do you? Let's just directly do it. Okay, so it's going to be A, B, C, A, D, right? Then can you make this to be A? Really? So it's just to directly draw one poly wire here. Let me see. Yes, you can, right? Because this is one line on the top and split into 1, 2, 3 in parallel. So they are equivalent, I believe. Right? So definitely no problem. Name it A. Because they're equivalent, so let's just name this B, C. No issues at all. All of these two. Yeah, AD. Equivalent, right? Just parallel transistors, no problem. Okay, done. You can label them so I know the signals, or you can draw the line. Sometimes it can be really messy really quickly because I have so many wires. If you label them, I can easily tell. Or you can factor A out, and then we'll compare which one is easier. Okay. So for this one, A is unlogic, so you have an A here. Think about the NAND gate. So A is in parallel with everything here, and BC and D for the NMOS is AND gate, so they should be in series. So I have A first, and then BC in series, and D. Is that right? non-gates NMOS NMOSes are in series with this and this, and here series and parallel. Yeah, correct. What about the layout? 1, 2, 3, 4, 5. Wait, 4. It's only 4 transistors on top. Promising? Let's try it. 5 nodes. So we get rid of 1A. That's why we are saving one transistor, which is going to save some space, I believe. So yeah, should be easy, right? If we introduce the wire here, then that's A, and 2 in parallel. We probably have to swap it, but let's take a look. Can we? Yeah, actually we have to swap it, I think. So in that case, it's A, this is D, and then 2 in parallel, right? Yeah, so to replace this one, you have to replace the connections here. So keep in mind, sometimes it always looks like that, then you probably prefer a single transistor on the top always, based on the experience we had. Okay, do this. D, B, C. Don't do this. Okay, then this one matches the schematic because this is A, this is D, and this is 2 parallel transistors, B and C. For NMOSes, go through A first. Go through A first. Can we just do this? So, oh no, let's use this as A. So let's do this. So this becomes A, and then BC in series. It's just the 2. You treat these 2 as one transistors, and it's just the 2 parallel transistors basically. So after A, you need 2 parallel transistors, right? It should be pretty straightforward. It's like this. So this actually occupies a smaller footprint on the chip because it only has 4 instead of 5. Let's label the ports. On the top, no problem. This is A, this is A. Okay. And this must be D. So in that case, we have D here instead of there. Can we move D to here? Is that possible? Move the ground here? Corner is ready for the midterm. What about these 2? So these are parallel transistors, doesn't matter, they're equivalent, so they can be B or C. What about these 2? Yeah. So let's just use this B and C, right? Okay, cool. Any questions on this? Good. Okay. Practice this a little bit more after the class. Let's look at adders. So on Friday, we talk about the logic, and we derived the logic actually for the full adders. And the conclusion was S equals A XOR B XOR CI, and the carry out equals A or B CI or AB. Sometimes you'll see an XOR logic here. And which one's better? Why it can be different? It resulted in the same logic. So if you look at CO's K-map, it was A, B, CI. And there's a pretty important concept you guys have a recap on, which is it's called static hazard. So they're both correct if everything works perfectly, but the physical world is just not perfect. All the transistors have time delays. That's why, whenever the other gate is not ready and you got a signal from somewhere else, it has all the glitches or the spikes, unexpected spikes in the circuit. It's called static hazard. Now let's see why that happens. So for BCI, it could be 00011110, right? That's all the possible inputs. And for the CO, I'm not doing the truth table anymore, but let's just plug in the numbers in here. It looks like a rocket launching. So if we just do this, this, and this, for example, okay? And now let's take a look at the logic here. If we just do this, what's going to happen? CO is going to equal to, for this one, getting singled out, but what is the logic here? What's the mean term here? A naught, BCI, right? For these two, A is always A, 1, but B is getting flipped or toggled, so B is cancelled. For these two, it will be A, what? B. So can we simplify anything from here? Can we combine these two? A not B. It's good to review this logic. Boolean algebra one more time. What's next? Can we simplify this further? Comes down to this logic. It could show up in the interview questions. If you are interviewing with NVIDIA, I mean, it's possible, right? It's very common. A or A not B. How do we simplify it? I actually couldn't remember how to derive it, but let's take a look, see if we can make it. If we do A, B, or B not, because this is 1, right? It's not changing anything. This may not work. I'm just trying randomly. Okay. Don't request for refund for tuition if this doesn't work. A, B, or A, B not, or A, not B. Does it do anything? Yeah, it's going to be A or B, but let's see how do we get there, right? If you have A or B, okay, and this equals A or B, oh, okay, and this is A or B, A not, or AB, right? And this becomes, let's combine these two, A, this becomes B, oh, wait, seriously? Where's A? A or B, A not, A or B, A not, AB, and combine these two, A factor out 1 or B is 1, not B, sorry. Yeah, so this is A or A not B, right? Okay, so they are equal. Okay, so we know that A or A not B equals A or B. So this becomes A or B, CI or AB. I think so this simplification here does the simplification here from a different logic. I mean, if you see other logic online, it may shows A X or B instead of A or B, CI or AB. I thought this was from this. If you group all the ones in this way, and you are getting this. But we didn't group it that way. We grouped these two together. And in that case, you're getting here, which is better because you're removing that static hazard in the middle, in the transition over here. But when we just use the other way to group it, but eventually we still get this, I think it's because we simplified it here from here to here. Are we going to get the same logic by having an XOR here instead of OR? If AB, CI for CO 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1. Okay. I want to see if this is correct. Okay. So A, X, or B and the CI, this is the same. So it's 0, 0, or AB is 0, 0, 0, 0, 1, 0, 0, 0, 0, and 0. And 0, no, 1, wait, 1, 1, this is 1, sorry, this is 1. And for the fifth one, it's 1, 0, and a 0. For this is 1, this is 1, so it must be 1. And this 0 and 0 and 1. And this must be 1. Let's add it together, see if you're supposed to get this carry out here. There's definitely no carry out for these ones, right? So until here, we got carry out. No carry out, carry out, carry out, carry out. Yes, it's actually right. So sometimes you'll see extra logic in the middle. Don't get confused. It's still correct. But we prefer OR because OR logic is way easier than XOR, right? Interestingly, on the website, if you search anywhere, it's actually most of this is being more often used. I don't know why. I mean, but this is definitely better. Less number of gates and no static hazard. It's just a lot better. But you can see, if you see extra logic in there, you should know it's also correct in terms of logic. Okay. So that's all the logic functions for the summation and the carry out. So how to build a flatter out of it? You can directly use the logic gates, okay, to build a 1. If we put everything in a 1 symbol, call it FA. We'll have a homework assignment to ask you guys to build a flatters on probably LT Spice. And that's CI. No. C0, right? Let's carry out. Is this a 1-bit flatter or 3-bit flatter? It's adding A0 to B0 and to C1, CI, and this equals S and carry out, right? Is this a 1-bit flatter or a 3-bit flatter? Hmm? One bit or 3-bit? It's a 1-bit because just adding 1 bit to the other 1 bit. That's carrying something else. For the first stage, you don't have any carrying. Carrying is 0. So if you want to build a 3-bit flatter, which is basically B2, B1, B0, that's a 3-bit binary number, right? And you're adding this to another 3-bit. And now you're getting a 3-bit flatter. So this becomes C2 is the final carryout, for example, and S2, S1, S0, that's the final result. You need all the summations for all the bits, and this is the final carryout. I only care about the final carryout as a MSB for the result. You'll see why. So the first stage is carry out. It's being served as carry in for the next flatter. And this summation is called S1. And this is another carry out, which is C1. What are these two? We are adding each bit to each bit for the 3 bits in here. You are actually doing this, right? You're adding LSB to LSB. You're adding A0 to B0. That's why you have A0 and B0. You are adding them together. And have a little carry out, which is C0, right? It's a carry out. And the carry out is being used as a carry in for the next bit, for the next flatter. or next bit actually. So it's going to be A1 plus B1 plus the carry in here, which is a carry out from the first one, from the previous one. So what are these two? Okay. And now you need a third bit. So what are these? What is this? What is this? What is this? Is this the final result? Is that possible to have 5 bits as the final result by adding 3 bits together? Is 4 bits sufficient to represent all the maximum numbers here? So what's the maximum 3-bit if are not considering negative numbers? What's the maximum 3-bit you can get? What's the largest number for 3 bits? No, 7. 111, right? So 111 is 7, right? So 111 plus 111, what's the maximum number here? 14, right? Is that 14? 7 plus 7 is 14. So 14 is what? Can you use 4 bits to represent 14? Yes. What's the maximum number for 4 bits if it's just a positive, no negative numbers? Come on. Fail the interview. Huh? So what is this? Yeah. What's the hex number for this? What's the hex number for 15? Come on. And this is hardware. This is actually microcontroller programming, right? We assign bits to pins or to registers. You are doing like register, for example, whatever, name it, okay? T0, okay? T0. And you're assigning 0xFF. So what is that? Yeah, 1515, okay? So FF assigned to this register is 0x, it's not OX. 0x means it's a hex number, right? It's a hex number. So FF means what? All ones. So how many bits is in the computer system, the CPU? How many bits? 8 bits CPU, right? Because all the registers are carrying 8 bits in it. If this is a sensor, it could be the accelerometer. It has 8 bits for each, or 1 byte for all the registers. It's just using bytes to carry all the information for the registers, right? So it's an 8-bit computer. Is this the final result? Do we need a C3 here as a MSB? No. 4 bits will be enough, right? Number of bits to represent 14 here, which is the largest number possibly you can have as a final result. Can we design a substructure out of this as well? I think we learned a little bit of this technology in embedded. For a lot of students, most of you haven't taken that yet. Connor probably the only one took it last term. But how do we design a subtractor out of this? But before we dive into the subtractor, we have to review the two's complement first. To represent negative numbers, use two's complement. How do we find the negative numbers for a positive number, binary number? So first, if the MSB is 1, So make sure this, you know this is signed, okay? It's a different number system now. Keep in mind. This is signed, it's not unsigned. So 100 is negative. Before we try to find out if it's what's the real number it is, but is this negative or positive in 2's complement? Keep in mind, if you have 1 as a MSB, it's always negative. Okay, no doubt on that. So, is this positive or negative? If the MSB is 0, it must be positive, all right? And now we just use a regular or the common sense to find out what is this binary number. What is this? Afraid of answering that simple question? What is this number? 3. So for positive numbers, it's not changing the rules. Only for negative numbers, okay? Because in the decimal number system, we add a sign in front of it, right? Like -10. But in the computer system, we are using, they're all based on the 2's complement number system. So a lot of times it's difficult to put a negative sign in the front, but how to register negative? It's a binary computer, right? It's only recognize 1 and zeros. So I have to use either 1 or 0 to represent the sign. So that's why human just invented this technology. It's not because, you know, if I put a 1 in front of 2 zeros, it becomes a negative number. It's not. 1 is just a 1. 1 is 1. This is 4. This is 4. Nobody can change it. It is 4 physically, right? But it's based on the computer system. We are able to manage it and to just use these 3 digits as a code. It becomes a code instead of number, actually, in the end, to be registered in the computer. So this becomes a negative number. It's not because it is negative. It is not negative. We're just using this 1 as a code over there, right? Make sure I understand what's going on. So physically, 0, 1, 1 is 3. Nobody can change it. It is 3. All right. So, but in 2's complement, we are defining -3 out of 3 by flipping all the bits and adding a 1 to it. That's how we convert that. That's how we find out the negative number from the positive number. That's just the rules. Just need to remember it. You guys did it in logic, but it's been a while. It's okay. So, like what I said, you have to flip all the digits and add a 1 to it. Keep in mind, okay? So for this one, we know this is 3. How do we find -3 out of 3? First, flip all the ones, all the bits. Becomes 100, right? And then add a 1 to it. So it's 101. So 101 is -3. Seems it's not making sense, but like I said, this is invented by engineers, and we are using this rule in the computer system, and this is -3 in the computer system, but physically it's not. How this could be -3? It's just a 101, right? It's 5. However, the computer system recognizes this number as -3. All right. What's the easier way to remember it or to find out what this number is? For example, 101, right? If I'm not showing you the conversion, the process in the conversion, if I just show you immediately, just show you 101, how could you figure out what that number is? It's unsigned. It's 2's complement. Whenever I'm saying it's 2's complement, it's unsigned. It's assigned, right? So in 2's complement, what this number is. Are trying to -1 and flip it, just converting it backwards. Can you do that? Yes, but just taking a lot of time, right? So if you convert it back, for example, I'm removing a -1 here, it becomes 100, right? And then flip all the bits. So I find out this is +3, right? So I know this guy must be -3. which is okay. It just takes time. What is a better way to figure that out? Yeah, so for actually the essential rule for two's complement, it's basically the MSB is the real value, real value, but negative, okay? It's the negative of the real value for the MSB. So for 101, this one used to be 4, but now it's negative 4. Right? And then you plus 1, it becomes negative 3. So you don't have to remove a 1 and then convert it back to find out what that number is. You just simply look at the MSB. So for example, if I give you this number here, it takes time to convert it back. But now let's just take a look at it. What is this number here in two's complement? Negative 8. So what are these two? 3. So what is this number? Okay. If we convert it back, remove 1 first, right? So it becomes 1, 0, 1, 0, right? And then flip it, 0, 1, 0, 1. Is this 5? Yes. So this is negative 5, no problem. What about 1, 0, 1, 0, 1? What is this? Easy, right? Two's complement is easy, super easy. Okay, so we know that if we are using a binary number, for example, B2, B1, B0 plus A2, A1, A0, this also equals B2, B1, B0 plus negative A2, A1, A0. No, right? So B minus A equals B plus negative A. We are not designing a subtractor, we are designing an adder, but we are adding a negative number of it. So before we want to save some space in the chip. So hopefully we can use the same adder to do both. So the question is how? Can we do both? This is just adding, it's not subtracting. We want to do subtracting as well. How do we modify it? There's a, if you look at the extra logic, if you use 1 XOR something like A, what is that result? You cannot directly find it out because you don't know what A is. But in digital circuits, A could be either 0 or 1. It's just 0 or 1, right? If A is 0, 1 XOR 0 is 1 because they're different. If A is 1, 1 XOR 1 is 0. So we are using, doesn't matter what A is, right? If you use 1 XOR something, right, this is something, what's the result? No, you have to look at these ones as well, right? If 1 XOR 0 got a 1, if 1 XOR 1 got a 0. Yeah, inverse A, inverse 1 actually, or inverse A actually, yeah, that's right. Okay. What about 0 XOR A? Can be 0, can be 1, right? 0 XOR 0 becomes 0, 0 x 1 becomes 1. It inverse what? It doesn't invert anything. Let's keep A, right? 0 XOR something is still that thing. So 0 XOR something is still that thing. But the 1 XOR something inverts it. Okay? Because for 2's complement, if you want to get 2's complement of all the A's, are you doing, for example, B2, B1, B0 minus A2, A1, A0, right? We need a 2's complement of all the A's because we're actually adding negative A. Okay? So we need a 2's complement of all the A's, all the A's. So to convert A's into its 2's complement or the negative number, we need to flip every single bit, like what we did over here. Okay, flip and add a 1. That's the definition of 2's complement, right? We need to flip every single bit and add a 1 to it. So we can do something here, right? Don't directly connect the A to it, but instead of that, we connect XOR gate to it and put A as the input of the XOR gate. All right. If we want to flip it, flip all the A's. What the other input should be. Want to flip it by using XOR logic. We need a 1. We need 1 to XOR A in order to flip it. So you can add a little control bit over here, right? You need a control bit, right? Can switch in between 1 and 0 in order to make this system a adder or a subtractor. What else do we need? Remember, 2's complement requires add a 1 as well. But you have to flip it and add a 1. So this guy's going to flip it, but it's not adding a 1. So you should add a 1 where? You should add a 1 from where? If you're just looking at this, right? Adding a 1 from where? From the LSB, right? Add a 1 from the LSB or at the LSB. Is that correct? You need to add a 1 at the LSB. You need to flip all the A's and you need to add a 1 to it. But you don't want to add a 1 here. You don't want to add a 1 here. It's in the middle, like these ones, right? You don't want to add a 1 in anywhere of these bits. You want to add a 1 here. So apparently it should be the carry in here, right? How do we make the connection? How do we make it work? After we switch it to 1, we flipped all the A's. And we still need to add a 1 to it. Yeah, will this work? It just works, right? We flip it whenever we switch it to 1. And also this one will be shorted to the carry in, is just adding to the system at the LSB. Then it performs as a subtractor. If we switch it to 0, what's going to happen? It will be adder. So A is gonna do what? Is A being changed or not? No, because if you look at the logic here, if 0 XOR A is not changing A at all, so A will pass through and reaches the input of the flatters, not being changed. It works just fine, okay? If you want to trigger that subtractor function, we just switch it to 1. You just need a little control bit over here, okay, to switch it back and forth. Depends on what you need in the circuit. Can we use a different switch instead of using XOR gates to do the same job? Yes, we can. But I think we don't have time to do that today. So let's work on it on Wednesday. And one thing I want to talk about. So when you guys laying out the circuits, please do not look at the layout. It's been a problem for many years. It's not just you guys. And I saw the same problem when Max and Seth, when they do the layout, but I just didn't, tell them. So they enjoyed duplicating the layout a lot. So I didn't realize that students will just directly look at the traces. Yeah. So if you see how I did it, what I did is I designed the stick diagrams, right? So for example, it's not something available on any of the tutorials. You are designing a totally different circuit by yourself. There's nothing like you can duplicate. So start with the stick diagram, okay? No, I should start with the logic simplification, and then you draw the all these AOI logic with the transistors. If you want to simplify the logic, and then the stick diagrams, and you should use different colors of markers. So it's in the old days, people just do that, but I think it's still working for now. You just find out different colors of markers to represent the polys, the metal 1, metal 2, metal 3. Okay, and then you just try to draw it on the paper to make sure none of the traces are getting shorted by yourself on the paper. And then you'll start the layout, just working try to duplicate everything on the paper, from the paper to your physical layout over here. That's how I did it. Okay. However, if you are just laying out, placing the parts into the window, and then you started duplicating all the vias and traces from the layout I have. First, my layout, I did it just based on my stick diagrams. It probably is not optimized. It's not the best one. If you design by yourself, it may look different. And also, when you design the traces by yourself, you can find out, like, sometimes you see there's a short circuit, so I probably you should start a via earlier, than later. You'll have to practice on that routing all the traces by yourself. It's something you should really experience instead of just staring at the traces and starting a via at the same place that I started. It's not going to worth the time doing that. I think it's a waste of time. You should do the layout by yourself instead of looking at mine. And sometimes this happened a lot for the past few years. So they are trying to duplicate these trees. However, you see this color is different, right? This is the purple color, it should be metal 2. But this part has a different color because I had metal 1 just underneath it. So that's why it's changing the color of the trees. A lot of times, since they are totally overlapped, and they are not figuring out there's a metal 1, so the student cannot pass that NCC check. So that's another drawback of just staring at it and duplicating it. Because I do have a metal 1 connecting probably here to here. But you cannot see it. You can see a purple. There's no other things. But I think I started the metal 1 here, right? From here to here. I just directly made a connection. But you cannot tell. You are thinking this is something else over here. Okay? Make sense? Hopefully you guys can follow a better practice on Tuesday. And so tomorrow I think we have a lab, which is going to be which lab we're going to work on. Is there a new lab? I think we do have a new lab. It's going to be this one. Buses. Okay. Cool. It's a good one. All right. See you guys tomorrow in the lab.